Hello and welcome to Calculus 2 here at Cañada College. My name is Lapuz. In this video we'll be doing checkpoint 6.3 coming from section 6.1. It says to represent this function f of x is equal to x cubed divided by 2 minus x using power series and find the interval of convergence. So let's start with what we do know. I hope we know that the series 1 over 1 minus x is equal to, this is our geometric series, 1 plus x squared plus dot 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 plus x to the n plus dot dot dot. Okay, so that is the sum as n goes from 0 to infinity of x to the n. So when n is equal to 0, we have x to the 0th power, which is 1, and then x to the 1st, x to the 2nd, etc. So now we should try to take advantage of this. Oh, but this, by the way, converges as the absolute value of x is less than 1. So it converges between 1 and 1. Let us take a look at how to manage this, how to take advantage of this series in terms of what we have here. Let's start with, let's take away the x cubed for now, and let's start with this expression 2 minus x. The idea is to somehow change this form to make it look like 1 over something. So let's imagine multiplying the top and the bottom by a half. And so when we multiply the top by a half, it's like having a 1/2 on top, or equivalent to having 1/2 all the way outside. I'm more concerned about this 1/2, and you distribute it. When you do, this will become 1, and this will become x over 2. Okay? So if I consider this thing as my x value, and then I have a constant 1/2 just sitting outside, then I can imagine that this is equivalent to the series as n goes from 0 to infinity of not just x anymore, but x over 2 to the nth power. Okay? All right, so that's our first step, and then now we want to incorporate the x to the third. And so to do that, we'll pick it up from here, or here, and that would be x to the third divided by 2 minus x. So that's the whole thing now. And I want to look at it from here, and that would just be an x to the third over 2 times 1 over 1 minus x over 2. So then I will have the series of x to the third over 2 times n goes from 0 to infinity of x over 2 to the nth power. All right, now what we can do is take this and distribute it inside, because this is equivalent to saying x cubed over 2 times, and then I will use this expanded out version. We have 1 plus x, but instead of x we're going to use x over 2 plus x over 2 quantity squared plus dot 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 plus x over 2 quantity to the nth power, and that is kind of like the symbol that we use inside of the sum. Now if we're going to distribute this, we're going to distribute it. We're going to have x cubed over 2 times 1 plus, now we have an x cubed times x, so that's x to the 4th over 2. Oh, that's 2 times 2, so that's 2 squared, plus, and then we have x cubed times x squared, so that's x to the 5th over, and then we have 2, and then 2 times 2, so 2 times 2 times 2 is 2 to the 3rd. Now if you can kind of see the pattern, it's literally multiplying this by x cubed. So we have x to the n times x cubed. We add the powers. This is x to the n plus 3. And then now we have 2 here, and then we have 2 to the n power, so this is going to be 2 to the n plus 1. So now this can represent our general power series, and I will write it down here as a sum going from 0 to infinity of x to the n plus 3 divided by 2 to the n plus 1. All right? All right, so this is our series, and we want to know what the radius of convergence, or the interval of convergence, is. So we can test this power series through the ratio test to figure out the radius of convergence. All right, and then eventually figure out the interval of convergence. So let's use a ratio test at this point. Ratio test of this series. So we are going to take the limit as n approaches infinity of the n plus first term. So this is to the x to the n plus 1 plus 3 divided by 2 to the n plus 1 plus 1 all over x to the n plus 3 divided by 2 to the n plus 1, all under an absolute value. So let's take the limit as n goes off to infinity, and here I will have x to the n plus 1 plus 3, that's x to the n plus 4, divided by 2 to the n plus 1 plus 1, so that's n plus 2, times the reciprocal, this is 2 to the n plus 1 divided by x to the n plus 3. All right? Now we have, let's see, we can count how many x's we have. We have n plus 4 and n plus 3 on top. I think we can get rid of a whole bunch here and then leave us with just one x in the numerator. And we haven't taken the limit yet, so let's keep the limit symbol here. And then we have an x in the numerator. And then if we see what happens with a 2 to the n plus 1, so there's one more extra 2 down in the bottom. So everything here goes away, and then you just have a 2 left over in the denominator. And I think that is your limit. There are no more n's, so this is just going to be x over 2. And technically, you can write it as the absolute value of x over 2 because 2 is positive anyways. Now remember that this is the ratio test, and we want that limit, and call it L, or I think they call it rho. So rho is equal to this, and we want to know when this is less than 1, because that's when it converges. So we could solve for absolute value of x. That's going to be absolute value of x is less than 2. And this turns out to be your radius of convergence. So your r, radius of convergence, is equal to 2. Okay, now that we know that, we have to check the endpoints for a radius of convergence. We know it converges here. We know it's going to diverge for bigger than this. Let's make a note over here. Diverges for absolute value of x bigger than 2. Now we don't know what happens exactly at 2, so we have a couple of points to check out. We want to check out what happens when x is equal to -2 and x is equal to +2. I think what we're going to do, since we're going to put that in for x is going to end up being an alternating series, so we're going to check the positive side first, and if the positive side converges, then it's going to absolutely converge, and if that's the case, then it's great, because now it'll absolutely converge, and we don't have to check the other endpoint. So let's see what happens. Let us take a look at this series, bring that series down, and we're going to put in the positive part first. So check Let's check x is equal to positive 2. And here we have the series of 2 to the n plus 3 divided by 2 to the n plus 1. And so this is a positive 2. It's not alternating. And let's see. This simplifies to the series. I think we can get rid of all the n's, and there's 2 extra on top. And this would be just the 2 squared in the numerator or something. Yeah, so this is just going to be a 2 squared in the numerator, and that's always kind of spelling trouble because by the divergence test, we take this thing, and it's a constant. There's no n's to put in because all the n's canceled out. We take the limit as n goes off to infinity of 2 squared, and that's just going to be 2 squared. And the whole point in the divergence test is that if your limit is not equal to 0, then it's going to diverge. So this is going to diverge. And I think that's the same thing that's, well, it'll be the same thing that's going to happen when you put the negative 2 in there. To the n plus 1, and this will give us again 2 squared, negative 2 squared, which again will fail the alternating series test. One of the alternating series tests is like the divergence test. You take the limit as n goes off to infinity of 2 squared or negative 2 squared. Oh, I think you want the absolute value of that, so it's just positive 2 squared. And if that limit does not equal to 0, then you're pretty much done. So they both diverge. Both diverge. So then your interval of convergence, again, drawing this number line is kind of neat. We have information at negative 2 and positive 2. We know that it's going to converge in here. We know that it's going to diverge out here. So that's by the ratio test. It's going to converge and it's going to diverge. And then now we just found out that the endpoints are not going to count because they're also going to diverge at the endpoints, so that's part of the divergence. And so the interval of convergence is going to be not including negative 2 to 2. Negative 2 to 2 not including the endpoints. Okay. All right, so we found our series. That's the first important part. And then we found the radius of convergence, and then we found the interval of convergence. Okay, I hope that helps. Good luck.